Okay, everybody, this is a quick review of the binomial distribution. The question is associated with a distribution where there are two possible outcomes, so look for that, either success or failure. The problem, the experiment, you are conducting n trials, so you're doing it several times, and that's supposed to be the word and, you are calculating probabilities associated with the number of successes that occur. So you're counting the number of successes when something is done so many times. Alright? So first, identification of the problem. So here's an example of a binomial distribution. The percent of Americans with at least some college education is 35%. A sample of 20 Americans is taken, and you're trying to determine the following. Determine the sample mean and standard deviation. So, first off, either they have at least some college education or they don't. One of two things. We will identify the probability of success, meaning at least some college education, as 35%. The sample size is 20, and so if you identify this as binomial, then you know you want to identify n, which is 20. P, the probability of success, is 35%. So Q is the opposite of that, meaning 65%. We want to determine the sample mean and the standard deviation. The formula for the binomial, the mean is going to be n times P. So n, 20 times 0.35 comes out to be 7. The standard deviation is the square root of NPQ. And so when you take the square root of 20 times 0.35 times 0.65 and you do your math, you're going to come out with 2.133. So the mean is 7. The standard deviation is 2.133. Remember, you can always stop the video. I'm going to be moving kind of fast through this. You do the actual calculations yourself. Stopping the video and confirming this, alright? Let me know if something's wrong. I hope I catch any mistakes I make, but this is totally unedited, and so keep that in mind. Alright. The next question is, what's the probability that 5 will have some college education? So, again, we're counting success, and we want to know the probability that we see 5 successes, meaning 5 people out of 20 have some college education. Well, for the binomial, if you're trying to calculate a probability that is equal to a number, you have to use the formula. C of 20 pick 5 times the probability of success, which is 0.35, raised to 5 successes times the probability of failure, which is 0.65, which means 15 failures because we have a total of 20 trials. Now, I'll just go over here. C of 20 pick 5, remember, it's 20, 19, 18, 17, 16. You're picking 5 things. 1, 2, 3, 4, 5. You're dividing by 5 factorial. 5, 4, 3, 2, 1. You do the math. You're going to get 15,504 multiplied to 0.35 raised to the 5th power. I got 0.0053 multiply 0.65 to the 15th power, and I get 0.0015. Okay, so again, that's C of 20 pick 5, 0.35 to the 5th power, 0.65 to the 15th power. Rounded to 4 places. Again, just try to keep as many decimal places as you can possibly stand. Okay, at least 4. Okay, and if you do your math, 0.13. So the answer to B is 0.13. Alright, moving on to C. So first off, let me just point out, if you are asked the probability of something that's binomial, and the probability you observe exactly so many successes, you're stuck with the formula. Okay? You have to use the formula. If you're given an inequality, I'm telling you, you can just go right to the binomial formula. All right? I mean, convert it to the normal distribution. All right? So now, in number C, we want the probability that we have at least 8 successes. And if we're going to convert this to normal, we have to be a little bit careful here. Because again, if we're looking at a number line and we want at least 8 successes, meaning we want to go in this direction, okay? We want to include the 8 because at least, so that means we have to drop down a half a unit, and so we're going to rewrite this as being equivalent to the probability of x being greater than or equal to 7.5. Our next step is to convert this to standard normal. Well, we already know that the mean was equal to 7. The standard deviation was equal to 2.133. So this here is equivalent to the probability of z being greater than or equal to 7.5 minus 7 divided by 2.133. If you do your math, that comes out to be 0.234. Again, I'm just using that z-score formula right there. X minus mu divided by sigma, right? Okay. So let's see. My next step is I now need to look this up in the table. Show yourself in the table. And again, I'm going to assume you can do this because this is the final. And if you can't get this at this point, I don't know really what to say, honestly. But if you look it up in the table, you're going to find out that this is going to be equal to 1 minus the probability of z being less than or equal to 0.234. Look it up in the table, do your math, and you get the answer as 0.4090. Okay? So, again, hopefully I looked up the numbers correctly myself, but I am under a kind of stressful situation right now to get this out to you, and my location is not the best place to get this done, unfortunately. But anyway, there you go. 0.4090. Okay, moving on to D. We want the probability that, let me leave this up here. We want the probability that fewer than 8 will have had some college education. So fewer than 8. So what we're looking for is the probability that x is less than 8. Once again, if we go over here and we think about the number line, we want to be below 8. Now, since we want to be below 8 and we do not want to include 8, we're going to have to, once again, go below 8 and drop down to 7.5. So this would be equivalent to the probability x is less than or equal to 7.5. Notice that this is really kind of the opposite of the one at the top. Okay, think about it. This is above 7.5. This is below 7.5. So if you do your math, or you can go through this same routine similar to what we did up here, but give it some thought. This is really equal to 1 minus 0.4090, which is 0.5910. So you can do it one of two ways. You can either walk through a similar routine like this by converting it to a z-score. You're going to get the same z-score. The only difference is you're going to be less than or equal to it, and that's the way the table works, right? And so if you looked up this value in the table, you would have gotten 0.5910. All right? So there's the answer to D. E, what's the probability that x is larger than 8? So the reason I'm doing this one, we want to be larger than 8. So here's 8. I want to be on this side of 8. But in this scenario, I want to be above the 8 So I'm going to actually add a half to this one. So it's good to draw a little graph, locate the number you are working with, then you have to decide which direction you're working in, and then whether or not you want to include the number or not include the number. I don't want to include the number, so since I am going off in this direction, I have to go above 8. So this will be equivalent to the probability x is greater than or equal to 8.5. So once again, I am going to go through the conversion routine. 8.5 minus the mean, divided by the standard deviation. Okay. If you're doing your math, it's equivalent to 0.70. The table only goes out to 2 decimal places, so I'll just leave it at 0.7. Once again, the table works in the opposite direction, so this is going to be 1 minus the probability of being less than or equal to 0.7. Show yourself when you do the math and look this up in the table that you come out with 0.2420. So here's the solution to E. So I'll just quickly review. That's the last problem. I'll give you the answers. For A, the answer is 2.133. For B, 0.13. For C, 0.4090. For D, 0.5910. And for E, 0.240. Okay? Thank you very much.